review what we did last week. So last week we mainly introduced the finite element method. And then we went into developing the first element. So I'll just quickly write down the expressions we had for this one element. So this is a two-noded element. This is node number 1 and node number 2. The length of this element is L. And we had some displacement at node number 1. We called that U1. And some displacement at node number 2. We called that U2. We had some forces applied. F1 and F2. And we assume that the x-axis is starting at node number 1, and we developed some expressions for this element. Now, we wanted to write everything in terms of the nodal displacement, so everything is linked to the nodal displacement. Now, this is the point of all the work we did last week. So first of all, we wrote the displacement across the elements as an expression. For this nodal displacement, we had 1 minus x over L and x over L multiplied with the displacement at the nodes. Then we had the strain expressed in terms of the displacement at the nodes. So this is minus 1 over L, 1 over L multiplied with U1 and U2. And then we had the stress expressed in terms of the nodal displacement. So this is sigma is equal to elasticity modulus multiplied with minus 1 over L, 1 over L multiplied with U1 and U2. And finally, we developed, this is we called the stiffness, this is we called the B matrix. So this is the B matrix. And then we also developed the relation between the forces at the nodes. So this is F1 and F2 related to the displacement through this expression, 1 minus 1 minus 1 and 1, U1 and U2. So this is pretty much everything we did last week. Into the displacement we are free to work with and change are the nodal displacements, and the forces are applied at the nodes. So can you consider a force that is applied here? For example, F3 here. This is something you cannot do because all the loads and the displacement are associated only to the nodes, nothing else. Otherwise, the element is not going to work. This is quite important assumption to remember. And pretty much everything we are going to discuss today is more or less related to this assumption here. I'll just go back to the slide which we last week. All right, okay. So this is example number 2. Now, example number 2, we have again a cantilever. The cantilever is fixed at one end and is loaded with 2W. Oops. And is loaded with 2W at the mid length, 1W at the end or at the free end. The length is L and the load is applied at L over 2. So this is the mid span. This cross section is A. The elasticity modulus is A. After the half span, after the first half of the span, the cross section would change to A over 2. Now we want to use the finite element method to solve this problem. We are going to follow exactly the same steps we did last week, but as you notice here, we have a load in the mid span, so we cannot work with one element. We need to have multiple elements. So we can, first of all, divide the problem into a mesh. This is the meshing process. And then we are going to divide this mesh into elements. All right, so basically we create nodes wherever we have something that would require a node. So this is a fixed displacement. We know that. We need to add a node in there. This is a load. We need to add a node in there. This is another load. We need to add a node in there. And there is another reason why we need to add a node here. That is the change in the cross section. So we have two reasons to add a node here. First of all, the cross section is changing. Second of all, we have a load applied. So we cannot apply the load. As I just said, we cannot apply the load at the mid span So it will have to be at one of the ends. And at the same time, as you mentioned, the cross-section would need to be uniform within one element. So we need to add a node in there. All right, so we have created this mesh. We are going to continue solving the problem following exactly the same steps, basically these expressions and exactly the same steps from last week. All right, I'm going to explain today how to build an assembly of multiple elements. And what I'm going to discuss today will apply exactly the same way to any type of elements or any number of dimensions. So usually if you have a geometry, I'll probably just add it here. You would have a two-dimensional or a three-dimensional geometry. You'll have to mesh that, create a mesh of triangles or probably quadrilateral elements. So what type of element depends on your choice. And then basically these elements will meet at the nodes. And these nodes will have numbers, just like node 1, 2, and 3. You will have 1, 2, 3, 4, up to the last node. And then you need to basically build the stiffness matrix for each one of these elements, basically build these expressions for each one of these elements, and then assemble them into the big problem. The expression or the procedure I'm going to explain today will work exactly the same way for this type of problems, just like it works in 1D. So I want you to understand it in 1D because it is very simple to understand in 1D. If you jump immediately to the two-dimensional or three-dimensional problem, it's going to be complex to understand, but in 1D is straightforward. So as I said, we build a mesh. The mesh is combined of nodes, and then we need to split this mesh into elements. So we have 3 nodes. This would mean we have 2 elements. So this is element number 1, and this is element number 2. This is node number 1, 2, and 3. Whereas for this element, we had node number 1 and node number 2. So I'm just going to write the number of the nodes because the number of the nodes is basically the key to build the assembly. And then this is node number 1 and node number 2. This is just like we have this element here. We had node number 1 and node number 2. So U1 is linked to node number 1, U2 is linked to node number 2, F1 is linked to the first node, F2 is linked to the second node. So everything is linked. I mean, when we build these expressions, everything is linked in terms of 1 and 2. Whereas when we come to this big problem, we have 1, 2, 3, we have multiple nodes. So we need to link this local degrees of freedom, these local numbers, to the global numbers. So if you look into node number 1, this is node number 1 here, is connected to node number 1 in element number 1. So I'm just going beside this one, I'm going to write another one. Where if you look into node number 2 in this first element, you'll see that node number 2 is linked to this node here. So this is linked to node number 2. If you look into the second element, node number 1 is connected to the node number 2. And node number 3 is connected to, or so node number 2 is connected to node number 3. As I said, I'm going to write the expression just exactly like I wrote them before when we solved the first example. So I'm just going to write the stiffness matrix for this element. You remember the stiffness matrix is E. So this is my stiffness matrix here. I said we call it K. And this is E multiplied with A divided by L multiplied with this numerical matrix. So I'm just going to write that for the first elements. For the first element, first of all, I'm just going to put the numerical numbers in there. This is not going to change. And then E for this element is equal to 1, A is equal to 1, L is equal to L over 2. So I'm just going to substitute these quantities into EA over L. E would remain E, A would remain A, L is L over 2. This is my stiffness matrix for the first element. So it's basically, if you just take these two to the top, it's going to be just the same. So I'm just going to move it to the top. So it would be written in this way. And in fact, I probably can just move it inside. So multiply these ones with 2 instead of having it in here. So I'm just going to remove it from here and put it inside the matrix there. So this is 2, minus 2, minus 2, and 2. So this is the stiffness matrix for my first element. Now I need to do the same thing for the second element. Again, I just use the numerical part. So this is 1, minus 1, minus 1, and 1. The cross section now is A over 2. The elasticity modulus is E. The length is L over 2. So I'm just going to write E, A over 2 divided by L over 2. If you want, you can cancel this one with this one. So I'm just going to write it as EA, as EA over L. Now I have the stiffness matrix for my local elements. I need to write the stiffness matrix for the big problem. Now, if you look into the big problem, you'll see 3 nodes. So I'm just going to create a matrix with 3 entries. Probably just make it slightly larger. And this matrix, to start with, is going to be empty. So I'm just going to insert zeros in there. And I'm going to put the numbers on rows and columns. So the first row and the first column are associated with node number 1. The second row and the second columns are associated with node number 2. And the third one is associated with node number 3. Now, if you look into these elements here, I just put the numbers first in black on them. We know that the first row and the first column are associated. You remember we have U1 and U2. So this is associated with U1. This is associated with U2. So this is associated with the first displacement. This is associated with the second node. And then if you remember on the other side, you have F1 and F2. So the first row is associated with 1 and the second row is associated with 2. This is local numbering we talk here. So this is the black numbers. If you look into this one, this is 1 and 2 again, 1 and 2. Now, the relation between these black numbers and the red numbers, I'm going to write them on top of this matrix here. So if you look into the first node, this is connected to the red one. The second node is connected to red 2. And the same is correct for the rows. If you look into the second matrix, you'll see that this is 1 connected to 2. And 2 is connected to 3. All right, now I have the local elements, or I have the stiffness matrix of these elements connected to the global nodes. So I don't need to remember the local numbers. I'll just get rid of them. I just need the red numbers. All right. Now, after you get to this stage, it's only a matter of reading a set of coordinates. You are going to read coordinates and insert them in the correct place. So let us now move these entries. First of all, if you look into EA over L is multiplied with this matrix and is multiplied with this matrix. So I'm simply going just to write it here. So whatever we have in there is also going to be multiplied with EA over L. I've just moved this one from here to here. Now I'm going to read the entries of the first matrix and insert it in the global matrix. I'll do the same for the second matrix. If you look into the first entry here, this 2 here, this is connected to 1, 1. So this is the set of coordinates connected to the first node. So this is 1 and 1. So I'm just going to take the 2 and insert it in here. So I have already 0 in there, so I'm just going to add 2 on top of that. So 0 added to 2 is going to be 2. If you look into this entry now, this is 2 and 1. This is 2 and 1. So this will be inserted in here. 0 added to minus 2, I will have minus 2 in there. If you look into the third entry here, this is connected to 1 and 2. So this is 1 and 2. I'm just going to do the same thing in there. So this is -2 added to 0, and then I have 2 added to 0 here. Now I'm done building the element number 1 into the global stiffness matrix. I'll just do the same thing for the second element. So the second element, I have 2 and 2. So the first entry, the set of coordinates you have for the first entry is 2 and 2. So this is 2 and 2. Now, I already have 2 in there, so I'm just going to add 1 on top of this 2. So this 1 is added on top of the 2. So this will be 3 then. And then I have 3 and 2. So this is a 3 and 2. So this is going to be 0 added to -1 is -1. And then I have a 3 and 3. This is +1. And finally, I have 2 and 3. This is -1. So now I have the stiffness matrix. I said the first row is associated with the first node, and the second row is associated with the second, and the third is the third. So for the first row, I have the displacement happening. Also, for the first column, I associate this with the displacement happening at the first node. So this is going to be associated with U1. This node is associated with U2, and this is finally with U3. All right, see, this is displacement happening at this node, this is the displacement happening at this node, and this is U3, U1 and 2 and 3. If you look into the rows now, the rows are associated with the forces. I mean, for the time being, I just assume that I don't have the forces, I don't have the displacement, I don't know nothing about the problem just yet. All right, just for the time being, I'm just trying to write the displacement and the forces in there. All right, so I have the displacements and I have the forces. This is the force vector and this is the displacement vector. I'm just going to remove these numbers now because I don't need them any longer. I'll just move this slightly closer. Yeah. All right, now I just continue solving the problem exactly the same way I have been solving or I did solve the problem from the last week. So first of all, I'm going to look into the displacement, find or identify which ones I know and which ones I don't, and then look into the forces and see which ones I know and which ones I don't know. Because this is U1 at the support, and I know the support is fixed, so U1 is 0. I'm just going to replace U1 with a 0 there. How about U2 and U3? I'm going to leave them as unknowns. Now let us move to the forces. What about F1? Do I know the value of F1? At the support, I know this is equal to the reaction, but at this stage, I don't know the value of F1. How about F2? If you look into the value of the force applied at the second node, and don't get confused between internal and external forces. We are looking, this force is there. If you remember the principle of virtual work, this is the external work done. This is not the internal. The internal work is happening on this side here. The external work is happening on the left side, and the external is only related to the external forces. So if we want to have the value at this node, this is the value of the external force, which is 2W. So I'm just going to replace this F2 with 2W. Now, how about the last node? The last node is the force applied at this free end, which is 1W. So I'm just going to write 1W in there. All right. So I have this system of equations. Just come back here. So 3 equations with the 3 unknowns. So the 3 unknowns are U2, U3, and F1. The 3 equations you get by multiplying this vector with this matrix here. So if you want to get the first equation, you multiply 0 with 2, U2 with -2, U3 with 0, and don't forget you have the whole thing multiplied with EA over L, and this would be equal to F1. The second equation is 2W equal to EA over L multiplied by -2 with 0 plus 3 with U2 minus U3. So this is the three equations, and these are the three unknowns. Zero. But okay, so I will solve the equations now. Now this is a system of equations, three equations with three unknowns. You are familiar with solving a system of equations, I assume. And you can solve it in any way you want. Now I'm going to do one way in this class. I mean, this is correct. The way I'm going to solve this system of equations is correct, and this is only math. All right. You can solve it in any way you choose. If you choose to follow the same way like I did in here, I'm going to do in this class, then you are welcome, and it is going to be correct. If you choose to do it in any other way, you'll get exactly the same answers if you solve it correctly. All right. See, the way I'm going to solve this, if you look into the right-hand side and the left-hand side, you need to distinguish between, I mean, usually when you solve a system of equations using a computer, you are going to either solve it for the right-hand side unknowns or the left-hand side unknowns. And solving it for both mixture of unknowns being on the right and the left is going to be very confusing for the computer. So you need to solve it for the unknowns on the left side first, and then you get the unknowns on the right side, just the same way I'm going to do in this class. So in order to be able to solve it for the unknowns on the right-hand side first, you produce what is called the reduced system. And the reduced system is you have a 0 in there. So the 0 is going to remove all the row and the column associated with the 0. So instead of solving three equations with three unknowns, you remove the entire first equation and the entire first column, and you are left with two equations with two unknowns, which is a lot easier to solve. So I'm just going to write down the reduced system. So this is 2W and W is equal to EA over L multiplied by 3 minus 1 minus 1 and 1 multiplied with U2 and U3. Sorry for this 2 here. All right, see, I solve these two equations, I get U2 and U3, and then I am going to come back and use the first equation again and get the value of F1. But for the time being, I'm just solving two equations with two unknowns, which is a lot simpler than doing three equations with three unknowns. I mean, if you have tried to solve the three equations, you'll see that it's easier to do the two equations with two unknowns. So I'm going to expand this into equations. So first of all, U2 is multiplied with 3, added to U3 is multiplied by 1. So I have 2W is equal to EA over L multiplied with 3 U2 minus U3. And then the second equation, you get it exactly the same way. So you have W is equal to EA over L multiplied by minus U2, 1 U3. So it is minus U2 plus U3. So these are the two equations I'm going to solve now. All right, so two equations with two unknowns. I'm just going to try and simplify it a little bit. So first of all, I'm going to multiply the entire equation with L and divide the entire equation with EA. So this is going to move the L to this end. And EA is here, and I can remove them from here. I do the same thing for the second equation, just multiply by L and divide by EA. So I'll have WL over EA. Now, I just remove the brackets. I don't need them anymore. Oops. I'll shift these things here. Get them closer. Okay, so I solved two equations with two unknowns. Just solve it any way you want. I can add them together. If I add them together, this is going to cancel U3. So I will be having 2WL over EA plus 1WL over EA. So this is a 3WL over EA is equal to minus U2 plus 3U2. This is 2U2. And U3 we cancel with U3. So I have U2 equal to 2, 3 over 2. I'll just divide the whole thing with the 2. And I have a value for U2. All right. Now, if I take U2 and replace it in this equation, I have a value for U3. So U3 now is just WL over EA. I will move U2 from this side to this side is going to be plus U2. And then I just replace the value of U2 here. So this is a 3WL over 2EA. Now, I want to add WL over EA to 3WL over 2EA. So I'll just multiply this with 2 and divide by 2. So U3 is then going to be 5WL over 2EA. So this is the value of U3, and this is the value of U2. I now can take the value of U2 and U3 and replace them back into the first equation. So now I can use the first equation. I'm just going to delete this from here. I'm going to replace the value of U2. Also probably just get rid of this line because I'm going to need it now. And this column here. I'm just going to replace the values of U2, U3 with the actual numbers of U2 and U3. So this is U2 is 3WL over 2EA. And if you look into the value of U3, this is 5WL over 2EA. Just remove this bracket here for a minute. 5WL over 2EA. And this is still the matrix there. And now I multiply 0 with this entry, this one with this one, and this one with this one, and multiply it with EA over L. This is going to be equal to the value of F1. So I have F1 is equal to 0, because 0 multiplied with 2, this is 0. First, I just write EA over L, not to forget that. It is 0 multiplied with 2, minus 2 multiplied with 3WL over 2EA. So this is minus 2 multiplied with 3WL over 2EA. And then I have 0 multiplied with 5, so this is 0. So if we look into this expression here, what you have in there is just simply, it's just simply EA over L multiplied minus 2 with 2 is going to cancel together. I'll be left with minus 3WL over EA and add it to 0. So this is only equal to F1. So if we look into this expression, EA is going to cancel away with EA, L is going to cancel with the L, and I'll be left with minus 3. So F1 is equal to minus 3. All right, so I have the value of the reaction, I have the value of the displacement, I get all the information I can get from the set of equations in here. Do you have any questions about this before we continue? Okay, then in this case, we continue to get the stresses and the strains. Now, if you look back, you see that this is the expression for the strain, and this is the expression for the stress. Now, I have two elements. For these two elements, I need to use this expression twice. First for the first element, and second for the second element. And it is exactly this expression in there. So I'm just going to write it down. I have the strain is equal to minus 1 over L, 1 over L, multiplied with U1 and U2. U1 is the displacement at the first node for the first element, and U2 is the displacement for the second node of the second element. Now let us look into the first element and see what are these values here. I mean, first of all, if you look into the first element, what is the length of the first element? The length of the first element is L over 2. So first of all, I need to replace these L's with L over 2. All right, I'll probably just write it. Just write it this way. So it is written as a capital L. Yes, go ahead. Yeah.
For F1, I think I missed something. Would it be equal to minus 3W, or is it minus 3?
It is minus 3W. Yes, sorry, it's my fault. Yeah,
oh,
you're
no,
absolutely right. Yeah.
Okay.
So we cancelled EA with EA, L with L. We are left with the 3W. It is minus 3W. Yes, thank you for that. Yeah. Any other questions? Okay. So I will come here. I write this as L over 2 and L over 2. Now, how about the displacement U1 and U2 for this first element? U1 is equal to the displacement at node number 1, and U2 is equal to the displacement at node number 2. We're talking global now. So this is equal to 0 and 3WL over 2EA. I'm just going to replace them in here. Just remove this entirely and probably create some space because I need it. It is 0, and then I have 3WL over 2EA, and this is the value for the strain. Now I'm just going to simplify this. This is going to result into 2 over L and minus 2 over L. So it is minus 2 over L and 2 over L, multiplied with 0 and 3. So 0 is multiplied with minus 2 over L, and 3WL over 2EA is multiplied with 2 over L, 3WL over 2EA. So the 2 will cancel with the 2, and the L will cancel with the L, and I'll be left with 3W over EA. So this is the strain I have in the first element. So this is the first element there. Now, I know the stress is just going to be the elasticity modulus multiplied with this. So it is elasticity modulus multiplied with the strain in the first element. So it is E3W over EA, and E would cancel away with the E. I'll be left with the stress being equal to 3W over A. All right, I've done this for the first element. I will repeat exactly the same procedure for the second element, just exactly the same expressions. I'm going to first of all replace, I'll probably just write it down in full, since this is the first example we do for multiple elements. So the strain in the second element is simply going to be minus 1 over L, 1 over L, multiplied again with U1 and U2. We go for the original element here. This is the second element. This is our second element here. And the second element, node number 1 will correspond to U2, and node number 2 will correspond to U3. And the length is again L over 2. So I'm just going to replace these into the expression. So L will be L over 2, and this is L over 2. I'm just going to simply write it 2 over L straight away. So this is minus 2 over L and 2 over L. And U1 is the value of U2, which is this one here, 3WL over 2EA, and then 5WL over 2EA. So I'm just going to write them down in here. It's 3WL over 2EA and 5WL over 2EA. multiply them together, and then you get this one multiplied with minus 2 over L. So it is minus 2 over L multiplied with 3WL over 2EA added to 2 over L multiplied by 5WL over 2EA. And the L will cancel away with the L. The 2 will cancel away with the 2. And you will be left with 3W over EA and then added to 5. So this is negative, sorry. This is minus, the minus sign, I don't need to forget that. So this is 5W over EA, and minus 3 added to 5. This is going to be 2W over EA. Now this is the strain in my second element. And to get the stress, I just simply need to multiply that with the elasticity modulus. So the stress in the second element is just elasticity modulus multiplied with 2W over EA. And this is going to cancel each other. And I will have 2W over A. This is the stress in the second element. All right. And then I have pretty much everything I need to have about this problem. And Muhammad is asking, are these the maximum amount of stresses and the strains in the whole members? Well, let us check. All right. If you look into the problem, you'll see that. Let us first of all look into the first element here, or the first section. I probably just to draw the whole thing down, and we try to work through the stresses. So you have a cantilever. The cantilever is fixed. You have two loads, one at this free end, this is W, and the other one is 2W. Now, from the stress point of view, the length doesn't matter. You know, the stress is always the force divided by the cross section. So no matter how long or small, and make no mistake here, the strain is quite related to the length, but the stress is not. It depends on what you are solving for, basically. But for the stress, what you care about is basically the force and the cross section. Now, cut this element at any point, or cut this beam at any point, and then take the equilibrium. I'm just going to forget about the reaction. I'm just going to look into the first section. I'm just going to cut this here, and then you have this section where you have the force is W, and then you need to have a W in the negative side in order to be able to keep it in equilibrium. So the entire force going through this element here is W, and then the stress in here is going to be W divided by the cross section. Now, what is the cross section in the first part of your element? The cross section in the first part is A over 2, so you need to divide by A over 2, right? So this is A over 2, or basically the stress is going to be 2W over A, which is the number we have for the second section. Now look into this first section, this element in here. Now, this section here, in order to be in equilibrium, I'm just going to draw it there. You have two forces active on it. So this is W, and this is 2W, all right? So to keep this in equilibrium, you need to have 3W in order to be able to just keep equilibrium. Otherwise, you will just lose the equilibrium. Now, this part of your beam, this entire part, is subjected to 3W as a value for the force applied to it. So basically, you have sigma is equal to 3W divided by the cross section. And what is the cross section in this part? The cross section is A. So it is 3W divided by A. And if you look into the stress we have in the first section, this is 3W divided by A. I mean, you can do this in any way you want. If you want, you can calculate the internal forces, basically the axial force, draw the axial force diagram. The axial force diagram is going to look like this. So you have W and then 3W. And this is how the axial force diagram is going to look like. And you can also draw it in this way. And you can always get the stress by dividing the axial force by the cross section. And you have that. All right. Okay, so any other questions? Yes, Mario. And I've explained about the stress and the strain. It is constant in this case, yeah. Any other questions? All right, so if you don't have any questions, I'm going to ask you a question. I'm going to ask you to solve the problem again. Now yourself, I want you to try solving it yourself and use a very similar problem, but instead of having L over 2, the length is now L. So I want you to solve exactly the same problem. The length has changed from L over 2 to L, and the force now is W and W. Before it was 2W, now it is 1W. Now we want to solve a problem where we have a distributed load. Singh asked about the gravity. And if you want to think about this distributed force, it can be something like a gravity. I mean, for example, if you want to consider it that, it can be that, but just have in this case uniformly distributed loads. So we have a uniformly distributed load, and we want to solve this problem using this element we have developed. So how to treat this case? Can we solve this problem using this two-noded element, you think? We have two suggestions. Kamal suggested we have the resultant, basically multiply. We have the distributed load to be small w, multiply w with L, have the resultant force and place it at this end here. And then Chloe suggested we do the same, but we place it at this mid-length. I think what Chloe suggested probably is more reasonable. I mean, if you move the entire force and you put it at this free end, is going to be a bit extreme. But if you put it in the middle, so this would be more representative. Now, the problem is if we do that, we cannot solve this problem using this element we have in there. So we need to kind of move midway between Chloe and Kamal so that we have the force, half of it placed at this node and the other half is placed at this node so that we have the forces placed only at the nodes. Remember, we cannot have any forces placed at the mid-length. If we want to do that, we probably need to have two elements. One element won't be enough. Now, we want to solve it using just one element. So this is why I would suggest probably divide this WL over 2, place 1/2 at this node and 1/2 at this node. So I'm just going to probably just do it here. So we have the element. I'm just going to write the stiffness matrix for this element. EA, probably just write it in the outside. 1 minus 1 minus 1 and 1. The cross section is A, the elasticity modulus is E, the length is L, so this would stay unchanged. We have U1 and U2 for the displacements at the nodes, and this is equal to F1 and F2. Now let us go with the assumptions we have just made. We have the force to be divided into two parts. This is WL divided by 2, and this is here WL divided by 2. Now, if you look into F2, F2 is equal to WL over 2. This is straightforward. Now, when you look into F1, F1 is not only WL divided by 2. Remember, you have a reaction in there as well. So it is actually WL over 2 plus the reaction, whatever the reaction is. I mean, at this stage, we still don't know the reaction, but we know that the reaction is going to be added on top of this WL over 2. So this is F1. I mean, I don't know one part of F1, so still I don't know F1. I'm going to consider F1 to be unknown and going to replace F2 with WL over 2. So this is WL over 2, and this is the system to solve. Again, I'm going to look into the displacement. U1 is 0, U2 is unknown, so I'm just going to replace this with a 0 as well, and solve for the system. Solve this system. Now, again, the same technique I used in the previous case, I can still apply here. So I just remove the entire row and the column associated with the 0, and I'll be left, including this guy here, I'll be left with WL over 2 is equal to EA over L multiplied with U2. All right, so basically U2 is then going to be WL squared, so I just multiply the whole thing with L, so it is WL squared divided by 2 EA, and I have the value for the displacement. If I want to get the reaction, I come back, just remove these lines because I'm going to need the equation now. So I will have 0 multiplied with 1, and then minus 1 multiplied with U2, EA over L. So it is EA over L multiplied with minus U2, so this is minus WL squared over 2 EA, and the whole lot is equal to F1. All right. Now I can cancel this L with the square, and EA will go away with the EA, and this will give me F1 to be equal to minus WL divided by 2. All right, this is the value of F1. Now, I am not interested in F1, I'm interested in the reaction. So I know that F1 is equal to this expression there, right? I know that F1 is equal to WL over 2 plus the reaction. I know the value of F1, I know the value of the reaction. I know the value of F1. I know F1 is equal to WL over 2 plus the reaction. So this way, the reaction is going to be minus WL over 2. And then I'm going to move this one to this end. So it is going to be also negative. It is minus WL over 2. And the reaction is going to be minus WL. So I have the reaction then. Now, if you check the problem, you'll see that the reaction should be equal to the resultant, just like Kamal said. So this is W multiplied with L, and we get the reactions to be minus WL, which is correct. And then we have the U2 is equal to the WL squared over 2EA. Now I'm going to continue and solve the stresses and the strains. So the strain is going to be minus 1 over L, sorry, it is plus now, 0 and U2, so this is WL squared over 2EA, 0 multiplied with minus 1 over L, and 1 over L multiplied with WL squared, so the strain is going to be 1 over L, WL squared 2EA, and the square again will go away with the L, I'll be left with WL over 2EA. Now, if you look into the stress resulting from that, I just multiply the whole thing with E, elasticity modulus. It is WL over 2EA, or just simply WL over 2A. So this is the stress I have. Now I'm going to discuss the stress a little bit. If you go to the problem here, and I want to evaluate the stress, I just draw it at the bottom. I have the problem, cantilever, fixed at one end and loaded with some distributed loads at this full length. Now the distributed load is W and the length is L. Now I know always the stress is going to be the force divided by the cross section. This is always for axial forces, for the axial loading, the stress is always the force divided by the cross section. So I want to evaluate the force. If you take X, I mean, this is only a matter of convention. I mean, you can take any convention you want, and you are always going to evaluate the stress exactly the same value for, I mean, you'll get exactly the same value for the stress. You are not going to get a different value for the stress. So it doesn't really matter what convention you use. As long as you are correct, your convention is correct, you'll get the same value for the stress. Remember that. Now I'm going to take the most convenient convention I can think of. I'm going to assume that X is starting at this point. So X here is 0 and it grows up to L at this free end. Now, if you cut the beam at one point so that this length is X, the force is going to be W multiplied with X. All right, so think about it. Right at the tip, the force is 0. You don't have any force in there. It's just right at the tip. X is equal to 0. When X will grow, the force is going to grow. Just like I did for the previous case, you have this cut in there, and this cut is moving because we have a uniformly distributed force. If you move this cut to this end, it's going to have no force at all. As you are moving, the force, which is going to react to that, so the reaction, I should be opposite direction, but anyway, the reaction is going to be W multiplied with X. And this is going to keep growing. So the amount of force that you need to have in order to keep the object in equilibrium is going to keep to grow up to this point is going to be WL, equal to the reaction, basically. So right at this end is going to be WL, and at this point is 0. So the stress is going to follow from there. I just draw the beam and draw the stress on top of that. I'll use probably blue for the stress. So right at this point, I have 0 for the force. X is 0, so this is going to be 0. And at this free end here, or sorry, at this fixed end, I have the full amount of the force. So this is W multiplied with L. So this is WL divided by A. So this is the full amount of force. Now in between, just like this linear equation, in between everything is moving in a linear way. Sorry, this is my bad. Yeah, should be reaching 0 at this free end. All right. So the stress is changing between 0 and WL over A. Now, if you look into the stress we have from the finite element method, I'm just going to highlight that. This is WL over 2A. All right, see, this is constant, WL over 2A. And if you look into this constant stress, you'll see that the constant stress is actually hugely overestimating the stress at the tip. Is assuming, based on the finite element method, you are getting a huge value for the stress. It's just, compared to 0, this is a very large number. Whereas at the support, where you have the maximum amount of stress, where you actually have the extreme stress, you are underestimating that by 50%. See, this is WL over 2A, and this is WL over A. So you are missing this maximum stress by 50%, which is an extreme error. This is something you cannot tolerate. Now, I want to ask you two questions here. The first question, why this error is happening? And the second one is how to improve it. Now, the second one, as I said, Harsh went ahead of me and answered that. You can improve it, obviously, if you do the many elements, which is absolutely correct. But I want to ask you then, the question remain, or the remaining question is why we are getting this error. So what do you think, where this error is coming from? Yes, I agree with all your answers. It is not that the finite element method is not working. It is your assumption is not representative. You are trying to do an approximation. Your approximation is too crude so that the answer is not correct. This is very important to remember. All right? See, the assumption you make is eventually going to be reflected, and the finite element method actually solved the problem correctly. I mean, what the finite element method has solved is not this problem. It's a completely different problem. What the finite element method has solved is this one here. This is what you solved with the finite element method. Now, the finite element method has solved this problem correctly and produced the exact results. I mean, the answers are exact for this problem. But is it the case that this problem actually representative for this one? I don't think so, because the error is huge. You are missing the stress by 50%. This is a lot. So to improve that, just like Harsh suggested right at the beginning, we are actually going to need more than one element. So basically, we need to have more elements. So I want you now to solve this problem one more time, but using two elements instead of using one element. So we're going to repeat the solution and using two elements. Now, how about the distributed force? The distributed force will happen exactly as we did it. So I will basically follow the same assumption like before to be consistent. You take the first half, take the resultant. Half of the resultant should be at this node, and the other half should be at this node. You take the second half, half of the resultant should be at this node, and the other half should be at this node. All right? See, this is how we are going to divide it. So take the first half, the length is L over 2, and the force is W L over 2. This is the resultant for the first half, and divide the whole thing by 2. So this is going to be WL over 4 and WL over 4. I'm just going to draw it here. So this is WL over 4, and this is also WL over 4. Now come to the second part. The second part is also, the length of that is L over 2. So you have WL over 2 divided again by 2. So it is WL over 4 at this node and WL over 4 at this node. Now, if you look into the second node, you see that WL over 4 is coming from the first half and WL over 4 is coming from the second half. So for this node here, you just use WL over 2. So in this case, the force vector is going to be F1, F2, and F3 are basically going to be, I'm just going to write them in full. So F1 is WL over 4 added to the reaction. F2 is WL over 4 plus WL over 4, so it is WL over 2. And F3 is WL over 4. So I want you now to solve this problem for the two elements. Just follow exactly the same procedure like we did in the previous example. Just do exactly the same steps. And I want you to do the full example. So find out the displacement. Sorry, the displacement, the reaction, the strains, and the stresses for both elements. All right, I want to have the strains and the stresses. Basically, I'm most interested in the stresses for the second element, for both elements. All right. And also, I'm going to share the answers now. All right, so I'm just going to discuss the results a little bit further. See, when we did one element, we have underestimated the maximum stress by 50%. So this is basically half. The red one is our finite element solution number 1. I'm just going to use green for the second case. In the second case, we have the stress to be 75%, or 3/4, and 1/4. So I'm going to write this answers in green. So you see the stress here in the second element is WL over 4. And in the first element is 3/4 WL over A. So this is WL over 4, and this is 3 WL over 4A. So if you look into the estimation now, the estimation has improved from 50% to 75%. So I'm still making an error. This error on the maximum stress is 0.25 or 25%. I have two questions for you. I mean, first of all, what number of elements do you need in order to get an error of 1%? I mean, talking about an acceptable engineering error, 1% is an acceptable error. So how many elements do you need to get 1% error? And then the second question is there any way to improve the results without having to use more and more elements? So these are the two questions. See, if you have this problem here, and you want to get the exact value for the stress, I mean, the exact value for the stress is something like this. And you are really interested in finding the stress at this point, right? This is where you are interested in finding the stress. So in this case, you have a very small element right to the point where you need to have the exact value for the stress. And then the other one can be very big. I mean, this is called the graded finite element. So whereas you have a stress concentration, for example, if you have a reentrant corner, you're trying to solve, let me just try to be more neat in my drawing, sorry. So for example, assume that you have some geometry and the geometry is loaded and you are trying to solve this problem. In this type of problem, you have a stress concentration here. It's probably as big as a stress singularity in there. So the stress is very high in there compared to anywhere else inside your problem. So in this case, you would use a very small triangle to solve this, whereas when you get away from this problem, you can solve this using very large triangles. So you can solve the problem with larger triangles away from the stress concentration, whereas close to that, you have very small elements. I mean, imagine instead of using one small element here, use small elements everywhere. It's exactly like using many small elements in here. You are going to get a curve that is much closer to this. But if you are interested in the peak value of the stress, then this one is going to give you a very good approximation. And then the other one is probably going to give you a crude approximation for the rest of it. You're still overestimating this by a huge amount, but the underestimate for this value of the stress is going to become a lot smaller based on how small this element is going to be. Usually, I mean, obviously in this problem, you would know that the stress is going to be maximum at the support. I mean, you don't know the value of the stress, but you know this is going to be maximum at the support. So this is, as an engineer, this is your judgment. So this is what you need to, I mean, taking someone who's not an engineer probably is going to use this brutal force approach and divide this into as many elements as they can, and they can solve the problem. Now, the difference between someone being an engineer with the background and enough knowledge about the problem is solving and someone who's not an engineer is this type of things. So your judgment and experience as an engineer will decide on how you are going to model this and how you are going to mesh this and solve this. All right. So this is, I think this is quite an important thing you need to be careful about. So again, this is, for example, when you have a stress concentration, such as when you have a reentrant corner, or if you have fracture mechanics at a crack tip, you have a stress singularity as well. So you need to have a very dense mesh right at the tip of the crack. So in these type of problems, you would know where exactly you have the stress concentration. So you bug this stress concentration with as many elements as you can. Get away from that. You can get away with larger elements. It doesn't really matter. But this will be a lot cheaper than solving this problem. I mean, think about if you have this length to be 0.01, and divide this into 100 elements, or divide this into two elements. One element is 0.01, the other one is 0.99. Now, doing this by hand is quite easy and possible, but doing 100 elements by hand is practically impossible. I mean, you probably spend a few months doing that because you eventually end up doing 100 equations with 100 unknowns. This is too much. Now, I want you to go back and try to do this with 3 elements, and you will start to see how complex this will become once you get more and more elements in there. So this is one exercise I want you to do in your own time.